Hello, Physics AP students. In today's lesson, we're going to, in a sense, more officially get started on the AP Physics C curriculum, albeit this is kind of like another pre-introductory lesson before we do start to get into any material related to electricity. This is actually a lesson that fall into more of the Physics C mechanics category. So there were actually two AP Physics C courses, Physics C Mechanics and then Physics C Electricity and Magnetism. Physics C Mechanics basically is just you take Physics 20, so the units on kinematics, dynamics, circular motion, gravitation, work, and energy, and the Physics 30 on unit on momentum, and you just reapproach everything from a calculus type perspective. Because you're really just doing the same material and approaching it from a calc perspective, it is a little bit dry, which is like a big reason why I choose to do the Physics C, electricity and magnetism, just because there's quite a bit of different stuff we can do in electricity and magnetism if we know a little bit of calculus, and also we'll do a unit on electrical circuits, which is a completely different thing. Okay, so in this particular lesson, what we're going to do is we're going to talk about work. We're going to distinguish between isolated, non-isolated systems, conservative, non-conservative forces. And the big thing we're going to try to get out of this is a relationship between the work done by an internal force on a system or within a system and the change in the potential energy of the system. Okay, so let's start off with this. So I've said consider an object moving along a path that has a length of r, well, magnitude of the vector r, from I to F. So I would be your initial position, F would be your final position, and a force acting on the object as a function of the position of the object r. Okay, let's just sketch what this looks like. Well, let's make it really simple. Let's just make the path in going from like an initial position to a final position a straight line. It does not have to be a straight line, but just for the sake of simplicity, we'll stick with this. All right, so what we have is we're starting at position I, we're going to position F, and vector R would be a position vector that points from start to finish. Okay, so that's like the displacement my object is going to represent. Now, what I want to do is along this path, there's going to be a force that's acting on an object as it moves from I to F. Now, there's no guarantee this force is constant. I mean, if this was a Physics 20 problem, if we were going from position I to position F, we would have to have a constant force. But now, because we have a little bit of understanding of calculus that is not necessary, so at the start here, the force could be like 20 newtons. Then it could switch to 15 newtons, then to 5 newtons. The important thing is that we have an equation for the force as a function of the position, and then we can handle it with calculus. Now, I did introduce this equation to you in terms of how we calculate the total work done when I did the math prep lesson on line integrals. So what we know is that work is equal to the line integral of the dot product F dotted with dr. Now, in brackets, I wrote down MEC1. That's an abbreviation for Mechanics 1. So if you look at the actual official College Board AP Physics C formula sheet, it breaks the equations down into a mechanics section, and it breaks it down into an electricity and magnetism section. We'll use a few of the mechanics equations. Again, like there's going to be a couple important ones we're going to look at today. But for the most part, we're just going to focus on the right-hand side of that formula sheet dealing with the electricity and mechanics portion. Again, if you don't have a copy of that formula sheet, you can just go on to D2L and you can print it off. So there's the math formula sheet, which is different from the actual official AP Physics C formula sheet. Okay, so what exactly does this line integral mean again? So what this basically means is take your path in going from I to F and break it into a bunch of little tiny chunks that we're going to call dr. Now, I can illustrate a few of them on here. So again, dr just means take the path r and break it into an infinite number of really, really small little chunks here, okay? Now, because you don't want to sit and watch me do this for another 20, 30 seconds, I'll stop doing it right there. I just wanted to illustrate that's what dr represents. It's just a chunk of this path r that's infinitely tiny. Okay, so I'll erase all this. Now, what we can also do is, because we have a vector dot product, you'll recall that if you have the dot product of two vectors, so A dotted with B, that is equal to the magnitude of A multiplied by the magnitude of B multiplied by cosine of theta. Therefore, if we have F dotted with dr, that would be the magnitude of F times the magnitude of dr multiplied by cosine of theta. Okay, where, again, dr just represents an infinitely small little chunk of the path. Okay, so again, we could draw an infinite number of those arrows. We're just going to draw a single little tiny chunk. Now, on that piece, we're going to draw, just hypothetically speaking, like what would the force be acting on that object at that point, okay? So I just drew the force up and towards the right. The direction right here is really not that important in terms of what direction the force points. I'll label theta, where theta is going to be the smallest angle between my force vector and my dr vector. Okay, now, one thing about this dr vector, because you might be wondering, okay, I get like breaking the path into a bunch of infinitely small chunks, but how do you know that dr vector points towards the right? Like, why can it not point towards the left? Well, here's how we do this. For the purpose of evaluating a line integral, we just assume, we kind of play dumb, and we just pretend like we don't really know what the direction of dr is, and we just assume it's going to be in the positive direction. So in the diagram that I've drawn here, the positive direction, if we're just going left or right, typically we associate right with being the positive direction, okay? So if I just flat out play dumb, I would just say that dr points in the positive direction is right. Now, the actual direction of dr will be identified by establishing correct limits of integration. So we can actually change our line integral here. So we actually have some lower and upper limits, which we actually did this on the previous slide. So the lower limit of integration would be Ri. So Ri would just be the position of the object initially, and the upper limit would be the final position of the object. So again, you'll see how this works out a bit more when we start to use these line integrals later on in the electricity unit when we get into discussions of electric potential. But again, if we're setting up a line integral, we just, again, play dumb with the direction of dr, and we just say it's just in the positive direction. And then the limits of integration are actually going to kind of correct the direction of the actual direction of the dr vector for you. Okay, but if you actually look right here, we can see we're going from point I to point F. Therefore, we are going towards the right. So that dr vector has been drawn in the correct direction. So no problem. Okay, now a little bit of a review of what it means to have a non-conservative force, and then we'll go into conservative forces, which are a bit easier to deal with, and what we're more interested in looking at. Non-conservative forces are forces that are external to a system, and we can also classify those systems that contain non-conservative forces as a non-isolated system. So good examples of non-conservative forces would be an external applied force or a frictional force. Now, typically when we talk about conservative or non-conservative forces, we then immediately make a connection between these forces and what effect that has on the mechanical energy of a system. So what non-conservative forces do is non-conservative forces cause the mechanical energy of a system to change. So the most basic example would be you have like a box, okay, and this box is at rest here. Now, if this box is at rest, you'd have absolutely no kinetic energy. Okay, so your kinetic energy would be 0. Now, if you apply a force in the box, Fa, you're definitely going to make this kinetic energy go up. So it's going to then increase. Your kinetic energy would then be a number that is greater than 0. And the way we define mechanical energy is equal to kinetic energy plus potential energy. So if I define my system here as just being the box, an external applied force on the system would cause the object's speed to increase. And if the kinetic energy goes up, EK goes up, then so does the mechanical energy. So typically an external applied force, usually what it does is it makes your mechanical energy go down. You could also have a frictional force here. So your force of friction would point in like the reverse direction. So you'd have the force of friction right there. What the force of friction would do is the force of friction would cause your kinetic energy to drop. So typically the force of friction causes mechanical energy to go down. But if we actually are able to get the box to move, it just means that the amount of energy that's being put in by the applied force is larger than the amount of energy we're losing as a result of the frictional force. Okay, but that's what non-conservative forces do. They have an effect on the mechanical energy of a system. Okay, I'm just going to erase this now. Now, going back to physics 20, this is like the most basic way I could identify what is referred to as the work energy theorem. So what the work energy theorem tells you is that if work is done by a non-conservative force, that's what the subscript NC stands for, that is going to cause the mechanical energy of a system to change. If the non-conservative force is an external applied force, it makes EM go up. If it's a force of friction, usually it makes it go down. Okay, so really like the equation is just taking what I said in words and putting it into an actual equation. Now, this is where it gets a little bit different. We never really talked about the path dependency of these forces back in physics 20. So a non-conservative force is what we refer to as being path dependent. So what path dependent means is it matters in terms of the path you take to get from one point to another. So if I give an example here, like let's say I have like position I, and I have position F. Okay, and one path would involve just going in a straight line here in comparison to like a much like longer path. Maybe I can go like up and down some hills here. Okay, and then I can go to point F. So if the person, for example, pushed a box along a longer path, the mechanical energy, a greater amount of mechanical energy be transferred into the box because you're applying a force, an applied force for a longer period of time, but you're also losing a lot more friction. So if you look at our two paths right here, we say that an applied force or the force of friction is a non-conservative force and path dependent because it depends on how long and like the actual distance you're pushing it for. If we take the bottom path from I to F, then we are not applying the force for as long, nor is the force of friction acting on the object as long. If we take the top path where we go through like all these little tiny hills and whatnot, we'd be applying exerting an applied force for a longer period of time, and we would also have force of friction acting on our object for a longer period of time. Hence, we refer to these forces as being path dependent. Okay, they matter in terms of the path you actually take. Okay, so let's just clear this. And that's what I said. So if you take the longer path, then you would transfer more mechanical energy into the box as a result of an applied force acting on the object for a longer period of time. But you'd also lose more mechanical energy because in the form of thermal energy, because the force of friction would be acting on that object for a longer time. Now, that's not really our focus here. We're a little bit more interested in conservative forces because this is what's going to have more of an application later on in the electricity unit. So conservative forces are internal to a system, which means they're generated from the inside. Good examples of internal forces that come from the inside of a system would be the gravitational force, because the gravitational force comes from like the objects, their masses specifically within the system. being subjected to a gravitational force. Or if you had a spring mass system, it would be a restoring force that's acting on an object as a result of a spring. So those are two pretty common examples of a conservative force. Now we're just going to focus on a gravitational force, and we'll leave restoring spring forces back in physics 20. Okay, so here's the example I have. I have an object. It's some distance, some height up in the air, and we're just going to drop it. Obviously, this thing is going to fall to the ground because there would be a gravitational force that pulls the thing straight downward. Now, conservative forces do not change the mechanical energy of a system. So the reason being is, like, if you looked at like this object here, and let's say at this position I dropped it, so maybe at this position you have like the kinetic energy of the object is equal to 0, and your potential energy is equal to, I'll make up a fake number, 10 joules, and you compare it to the object the instant before it hits the ground. So the instant before it hits the ground, you would have no potential energy if you define the reference axis as being the ground. But all of your potential energy has then been converted into kinetic. So you'd have 10 joules here. And your mechanical energy, if you just add the two of them together, would be 10 joules and 10 joules. So my internal or conservative force, the force of gravity, had no effect on the actual mechanical energy. The mechanical energy at state 1 was equal to the mechanical energy at state 2. Now, what I do want to focus on, though, is what effect does this have on the kinetic and potential energy of my system? So it turns out if the only force acting on an object in a system is a conservative force, it is going to cause the kinetic energy of the system to increase. Now, I want you to note right here, we're using a different variable for K. So with the AP Physics C, instead of using EK for kinetic energy, we're going to use capital K to represent kinetic energy. Okay. So in this case, if the only force acting on this thing is the force of gravity, this conservative force is clearly going to make the kinetic energy of the object increase because its speed's increasing as you approach the ground. Now, what this non-conservative force, what this conservative force also does is it causes the potential energy of the system to drop. And we can see that. This conservative force Fg is the only force acting on the object. As the object gets closer and closer to the ground, it starts to lose more and more potential energy because its height is decreasing, and that energy is being converted into kinetic energy. Now, conservative forces are what we refer to as being path independent. So path independent means it doesn't matter how I get from one point to another. Okay, so let's consider two paths here. So path 1 would just be this object falls straight down. Path 2 would be, instead of letting it fall straight down, I would just chuck it a little bit more towards the left. So maybe path 1 would be I chuck the object straight down, and then path 2 would be I just chuck it a bit to the side. Okay. Now it turns out that it doesn't matter which path you actually take, because both paths result in the same change in kinetic energy, and they both result in the same change in potential energy. So again, if you just look at this right here, like if we look at our potential energy at the top, so I can make up some different numbers here. Like let's say we actually chuck this thing at like a certain speed. So maybe let's say like 5 joules, and your potential energy, EP, is 15 joules. Although we should use a different variable here. So we use K for kinetic energy, and we use U for potential energy. So what I could write here is I could say U1 is 15 joules, and I could say K1 is 5 joules. Now, regardless of what path you take here, okay, if this system is isolated, so isolated means we don't have any of those non-conservative forces like friction or any external applied forces, whether you end up here or whether you end up here, you're going to have your potential energy at state 2 is equal to 0, which means that your kinetic energy at state 2, regardless of what path you take, would then need to be 20 joules. Okay, so you put the two of them together, you get your mechanical energy. So at state 2 here would be 20 joules. And then here, your mechanical energy at state 1 would be also 20 joules. So again, it doesn't matter which path you take, because regardless of the path you take, your mechanical energy is going to be a constant, and your change in kinetic energy and your change in gravitational potential energy are going to be the same. Therefore, conservative forces are path independent. Doesn't matter the path you take here to get from position I to position F. Okay, we're going to expand upon this a little bit. So, isolated systems are systems that only have conservative forces in it. So an isolated system would not have external applied forces, nor would it have any frictional forces. Now, what we observed on the previous slide is that the work done by an internal or conservative force will do two things. So if we go back here, work done by an internal force. So this internal force is going to be the force of gravity. So what does an internal force do, or work done by an internal force? It makes kinetic energy go up, and it makes potential energy go down, if that's the only force acting on the system. Now, I'm going to focus exclusively just on what's happening with the potential energy. So if the only force we have acting on an object in a system is an internal or conservative force, it will always make the potential energy of the object decrease. I'm going to take that statement and I'm going to write it as a mathematical equation. Okay, so what this means right here is the work done by an internal force. Internal forces are conservative forces. What do? Well, they cause the kinetic energy of an object system to go up, but I'm going to focus on what happens to the potential energy. So what they cause the potential energy to do is go down. So that's why you see this negative sign here. So work done by an internal force will cause a decrease in the potential energy of an object. Okay, so that's why that negative is there. Decrease. Now I'm just going to take this equation and just divide both sides by -1. And I'll come back to using this format of the equation in a moment. So if I do that, I would just have delta U, which is your change in potential energy, is equal to negative work done by the internal forces. Okay, so we'll come back to that later. Now, what I'm going to do is I'm going to take my work equation as a line integral, and I'm going to derive an equation that we're familiar with back from physics 20 for potential energy. So I'm going to do a bit of a derivation here. Okay, so let's consider an object, so that's that blue sphere, that has a mass of m, and it's going to fall from a position. So the initial position of the object would be at the very top. Okay, we're going to call this Ri. So Ri means the initial position of the object, and we're going to say it's at a height of positive h1. Now, this is going to fall to a height somewhere above the ground that I'm going to call Rf. So Rf just represents the final position of the object. And we're going to say the final position of the object is at a height of positive h2 above the ground. And we're establishing the reference axis here is that my position is equal to 0 if I'm on the ground. Now, what I want to do is I want to calculate how much work is done by the force of gravity. So the force of gravity is an internal force in making this object go from position I to position F. Okay, so we're going to set up our line integral. So the work, and I have a little subscript g here, so that means the work done by the force of gravity is equal to the line integral when I go from my initial position, so my initial position is h1, down to my final position, which is h2, and then work is the dot product of force with dr. Okay, we'll be more specific here because we're talking about the work done by the force of gravity. Therefore, we'll change F to Fg, and we're going to dot it with dr. Now, if we expand this as a dot product, so the dot product of Fg dotted with dr would be the magnitude of Fg times the magnitude of dr times the magnitude of cosine of theta. Now, what we have to do here is we have to identify what the direction of dr is. The direction of Fg, if you look at the diagram, just points towards the bottom of the page. Now, as I said with dr, the direction of dr, we just played dumb with it, okay? So r would actually be a vector that goes from position I to position F, okay? That would actually be the vector r. But again, the vector dr, we just play dumb, and we always assume it points in the positive direction. So what's the positive vertical direction? Well, that would be up. So if I took this path, so r here, and I broke it into a bunch of little tiny chunks, okay, of the path, that's what dr is. But for now, we're just going to pretend, we're going to play dumb and pretend that dr just points in the positive direction, okay? So it points up. We'll use the limits of integration to correct the direction in a moment, okay? So in this case, a couple of things. If we're in a uniform gravitational field, Fg is a constant. So like the weight of this object at point I and the weight of this object at point F are the same. Okay, so if my object's weight is 20 newtons up here, it'd be 20 newtons down there. Okay, that's a constant, which is important because it means we can pull it out of the integral. Theta would be 180 degrees because Fg points down and dr points up. Okay, so we can change this to, let's pull Fg out of the integral because it's constant. Okay, so it comes out here. So to have Fg is the line integral from h1 to h2 of dr times cosine of 180 degrees. Now, you still might be annoyed at the direction of dr. You're like, why is dr pointing up? Like, clearly my object is going down. Well, that's what the limits of integration are going to do. The limits of integration are going to fix that for us. So the limits of integration are going to tell us, well, we're actually going from h1, which is up here, to h2, which is down there. The problem is that if you actually say dr initially points down, and then you apply the limits of integration, you kind of end up undoing the correct direction, because it's in a sense what you're doing is you're applying the correct direction twice, because you'd be saying that dr is down, and then the limits of integration also telling me I'm going down. So if you have like down of down, I suppose that would actually be up. I don't know if that makes any sense. It's very odd wording. Okay. Long story short, just take dr, assume it's in the positive direction. The limits of integration are going to correct it because the limits of integration tell me what direction you're actually going. Okay, cosine of 180 degrees is -1, which means we can also pull this -1 out of the integral because it is a constant. Okay, so it goes out here. Therefore, now we're left with -Fg in the integral when I go from h1 to h2 of dr. Now, we don't need to actually evaluate this line integral. We just need to understand what it physically represents. So what this is saying right here is it's saying take the vector r, which goes from like I to f, break it into a bunch of infinitely small chunks, and then just add them all back together. Okay? So if I took the vector r, I broke it into a bunch of infinitely small little chunks, and then I added them back together, what would that represent? Well, it would represent this distance in going from h1 to h2. Okay, so we can actually get there in a second. I suppose if you wanted to, you actually could evaluate this integral because this would just be the integral of dr. So it would just be finding the integral of 1 dr, and the integral of 1 dr with respect to r would just be r. Okay, but this line integral does actually represent this distance in going from I to f. Okay, if we evaluate this though, it'd be -mg r evaluated from h2 to h1, and then we get -mg h2 minus h1. Okay, and that's what I was saying here. If you take this entire line integral and you just question for a second what it actually represents, okay, So again, what it means is take this distance, break it into a bunch of infinitely small chunks, add them back together. Well, that would just be the distance in going from h1 to h2, which is h2 minus h1. So either way, actually, whether you integrate it or whether you just like look at it and just identify what the line integral represents, you get the same result. Okay, I'm going to take h2 minus h1. I'm just going to change it to delta h. So now what I have is wg is equal to negative mg delta h. Now I'm going to go backwards, and I'm now going to make use of this equation, okay? The one that tells me delta u is negative w internal. If delta u is negative w internal, and I want to figure out what delta u is equal to, then wg is the internal force. So to figure out what delta u would just be negative multiplied by this right here, which would actually give you delta ug is equal to mg delta h. Does that equation look familiar to you? It should. Okay, our gravitational potential energy equation is EP is equal to mgh, or if we wrote it in delta notation, my delta EP is equal to mg times delta h, or if we write it in AP Physics C notation, it would be delta U is equal to delta mgh. So essentially what I did right here is I derived this equation we were using all the way back in Science 10. EP is mgh, and I did that using the definition of work as a line integral. And I also utilized this fact that work done by an internal force in a system will cause my potential energy to decrease. Now, that's if you have a uniform gravitational field. But what happens if you went from point I to point F and the gravitational field changed? So, I mean, if we're close to the surface of the Earth, this is no problem. Like whether I'm at position I or position F, my acceleration due to gravity would be 9.81 meters per second squared down. But if I like started off in like outer space and I came close to like the surface of the Earth, then my gravitational field is actually going to differ. Now, that would be a big problem because that means we can't pull this guy out of the integral. Okay, so we're going to have to take a bit of a different approach to figure out what this looks like. Okay, so let's try to do this. Okay, so I'm going to set things up a little bit more differently here. Okay, so here's what I have. I said we have a planet, which has a mass of m1, so this could be like the Earth, except this time we're going to start off in outer space. We're not going to start off in like some region that we're close to the actual surface of the Earth. Okay, so I have an object that's m2, so this could be like an astronaut or something, just like sitting, I don't know, floating, I suppose, in outer space, although it's probably not the best thing for him to be doing. Okay, so obviously the force of gravity would try to pull the astronaut towards the center of the Earth. Okay, so we have a planet of mass m, a small object of m2, and we're going to establish, I want the reference axis to be located at the center of the planet. So the reference axis, where my position is 0, r of equal to 0 at the center of the planet. Now, what I'm going to do is I'm going to calculate how much work is done in moving this guy, so M2, from an infinitely far location. Okay, so the question right here is, well, how far away is this astronaut or this spaceship or whatever from like the Earth? Well, we're just going to say it's infinitely far away. Okay, so we're going to say our initial position relative to my reference axis is located at positive infinity. I mean, it doesn't have to be infinitely far away, but it's really, really far away. Okay, quite far away from the center of the Earth. And we're going to move it to a final position that is located at positive r from my reference axis. Okay, so we're going to move this guy from this position, infinitely far away, to this position, where we would be a distance r from the center of the planet. Okay, so the distance r would just be measured from here. Okay, so we're going from infinity to this position, which is located positive r from the reference axis. Okay, let's calculate this. So the work done by the gravitational force would be equal to the line integral from my starting position, which is I'm infinitely far away, to a position r from the center of the planet. And then I'm going to take the dot product of Fg with dr. Okay, so we're going to expand this. And when we expand it, we're going to have the integral from infinity to point r of Fg magnitude dr magnitude times cosine of theta. Now, we have a couple of problems here. So the first problem is that Fg is not a constant. If you calculated the force of gravity between this mass and the planet far away compared to when it's closer, the closer I get, the bigger this force gets. So this is a problem, okay? Because now we can't pull it out of the integral symbol. So we're going to have to be a bit more clever in how we deal with the fact that this position is actually changing. Now, dr, again, we play dumb with the direction, and we start off just by saying this dr vector always points in the positive direction. Okay, so if you have a horizontal distance between m1 and m2, and we play dumb, what's the positive direction? It's towards the right, okay? Now, I know that m2 is actually moving towards the left, but the limits of integration are going to correct that, because the limits of integration tell me we're going from infinity to position r, so that's actually towards the left. So again, the limits of integration correct the direction of what dr is. Okay, so that means that theta is 180 degrees. Therefore, cos of theta is -1. But we still have this problem with Fg. Now, what I want to do is I want to replace Fg with an equation that I could actually use to calculate this force. So if I have mass 2 here, and I want to know what is its weight here in comparison to its weight there, which equation from physics 20 could we actually use that would relate the force of gravity to how far away I am from the center of the planet? Now, I'm hoping that you identify very quickly it's Newton's universal law of gravitation. So my equation would be G m1 m2 over r squared. So what I'm going to do is I'm going to replace magnitude of Fg with this equation. Okay, so what this looks like now is this would be work done by the force of gravity is equal to the integral from infinity to position r. Again, position r, we're not really defining where it is. I mean, it could be like any position from r equals 0 to all the way where mass 2 is located. And now we're replacing Fg with Newton's universal law of gravitation, gm1 m2 over r squared. And this -1 here, we're just going to pull it out of the integral. Okay, so it goes out to the outside. Now, what I then want to do is, okay, are there any other things that are constant that I can pull out here? Okay, well, capital G is the gravitational constant of the universe, so that can definitely be pulled out. M1 is the mass of a planet. Unless the planet's exploding, the mass is staying the same. And M2 is the mass of my object, which presumably is also staying the same. Now, R is changing because as we go from infinity to position R here, the distance from the center of the planet to where the person is changing is going to change. So we cannot pull out the R squared from the integral. No problem though. Okay, so we'd have Wg is equal to -g m1 m2, and then the integral of from infinity to r of 1 over r squared dr. Now, this time around, we actually do have to evaluate that integral, but that is not a hard integral to evaluate. Okay, so what I'm going to do is let's take this and rewrite it more in that like power form, where I have like the exponent or the power on the top of the equation. So if we wrote 1 over r squared and put it up to the top, it would just be r to the -2. So this would look like Wg is equal to -g m1 m2, and then the integral from infinity to r of r to the -2 dr. Okay, so what I need to do is just figure out what's the antiderivative of r to the -2. Well, we can use that simple rule that tells us if we have the integral of x to the power of n, that would be equal to 1 over n plus 1. x to the n plus 1. Now, we're using r here instead of x, but this would be r to the negative 2 would then be equal to 1 over, okay, so what's the value of n? It's negative 2. So it would be negative 2 plus 1, x, not x, we're using r here. So let's erase that. Okay, r to the negative 2 plus 1. Okay, so this would then be r to the negative 1 over negative 2 plus 1 be negative 1. Or we could just write it down as negative r to the negative 1. Okay, so that's my evaluated antiderivative. The evaluated antiderivative would just turn into negative r to the power of negative 1. Okay, let's clear all this ink off the slide here. Okay, let's evaluate this. Although I think before we evaluate it, we're now going to turn the r. Well, first of all, we can pull this negative out. Okay, this doesn't have to be here. Okay, so we can pull that out of the integral. And then we'll turn the r to the negative 1 back into having positive exponent. Okay, so this would be the negative times a negative would be positive. So you'd have g m1, m2, and then 1 over r. And we're going to evaluate that from infinity to r. Okay, so that would then turn into gm1, m2, and then when we evaluate that, that'd be 1 over r minus 1 over infinity. Now you might be wondering, how the heck can I actually evaluate an infinity? Well, just think about this for a second. If you take 1 and you start to divide by progressively larger and larger and larger and larger numbers, like for example, go in your calculator and type in 1 over like a billion or something like that, and see like what that number is close to, 1 over an infinitely large number is actually going to be equal to 0. So we can simply get rid of that term. Okay, so that's going to tell me WG would just be equal to G M1 M2 over R. Okay, so what this equation does is it says the work done by the gravitational force here in going from point infinity to position R. So again, position R is just located a distance r from the center of the planet, would just be gm1 m2 over r. Okay, and r would just be this distance right here. Okay, we're coming to that position. Now I'm going to take that other equation that tells me that work done by an internal forces causes the potential energy of a system to decrease, or if you write it in the other format, delta U is negative W internal. So we're going to plug in this right here, and we're going to get an equation that tells me delta UG is equal to negative GM1 M2 over R. Now, this seems like a really weird equation, because if you're looking at it, you're like, okay, so it's saying the change in the potential energy of an object is negative GM1 M2 over R. So usually the immediate question is like, why is this negative? Well, look at what's happening here. So what we actually did here is this represents the change in potential energy when we go from an initial position of positive infinity to a final position that's located a distance r from the center of the planet. Okay, so that's located somewhere right here. So we're going from positive infinity to RF. Well, what happens to your potential energy when you get closer and closer to the planet? It's the same thing as if you have like an object and you just drop it straight down. If you dropped an object straight down, its potential energy would decrease. So when we go from positive infinity to a position R from the center of a planet, our gravitational potential energy would drop, hence the negative sign there. Now, we're not really going to need to use this equation in our course, but this concept is going to be very, very, very similar to something we talk about a little bit later. You'll recall, even back in physics 30, there were a lot of direct connections between gravitation and electricity, and we're going to have to use this whole concept of starting at infinity and moving to like some other position we start to look at electric potential in a little bit more detail, because we barely scratched the surface of what electric potential is in Physics 30. All right, so that's it for this lesson. There is no homework assignment attached to it. Like I said, it's just kind of just like a pre-lesson that's going to set us up to do some things later on in the unit. So all I would do is just ensure that you've completed the 7 math prep quizzes for the calculus and the vector math. And I made a note on the differential equations lesson, so quiz. So if you start the differential equations quiz, it's one question where you have to match 6 differential equations to the solution of the differential equation. Now, you can technically do that with trial and error. Like you can take you can take like any of the 6 possible solutions, like y equals, you can plug them into the differential equation and verify, and that definitely could solve the matching problem for you. However, that's not really of particular use to us. What you really need to do is practice using the separation of variables technique to take those differential equations with the given initial condition, and then do separation of variables, and then all the fun math to get the value y properly isolated. Okay, so you're doing it with algebra and with calculus. Okay, and then in the next lesson, we will finally, after these 7 math prep lessons and this other pre-AP Physics C lesson, we'll actually get back into revisiting electricity, and we'll start to do it by looking at some of our equations, but approaching it more from looking at our vector math, our 3-dimensional vector math. And I'll talk to you then.